under normal circumstances, we would give you 4 assignments. That's 10%. This is under normal circumstances. 1 midterm, 30%, and final, 60%. I think we're going to change for this in this environment. We're going to change the assignment to a quiz for 10-question multiple choice quizzes on Canvas. So and I'm going to convert the final to an midterm. Also on Canvas. All of these are going to be on Canvas. Subject to change. I am, like I said, it's subject to change because the situation right now is very fluid, and every day something new happens, something changes, and you might hear in the middle terms everybody, all right, everybody come back to school. Like I said, this situation is fluid, so don't quote me on the what I have here, but that is my idea for now. All right.
Okay, sir.
All right. So like I said, I will put I have some textbook. I have 2 textbooks, Signals and Systems. Charm series. And the other one with is that the other one with the same. I will post them in the group at the end of the class, as well as I will be posting the course outline at the end of the class. 6 major topics in the course outline that we are going to do. It's chapters 1 to 5. Let me have a Signals and Systems book here. Like I said, I have an electronic copy that I will post online. In this book is chapters 1 to 6. Sorry, lie. 1 to 7. And in the other book that I will post is chapters.
Sir?
Okay. Yeah.
Question, sir. So regarding updates for the class, so everything will be in the WhatsApp group?
Yeah.
All right, sir.
All right. So this is, that is 1 to 10. All right. So that's basically it. Like I said, any questions that you want to post it, put it in the WhatsApp group. And I will be sending the things to the WhatsApp group as we complete the class today. All right, so So what is this course all about? Well, it's a maths course, although we don't say it's a maths course. And if I tell you that, if I told anybody that I said it was a maths course, then they would take me to task. So it's not a maths course. It is a course that has a high mathematical content. All right. So what the signal and system is all about? We call the input a signal. Input to a system is called a signal. And the system manipulates the signal to produce the desired output. So the input is a signal, system manipulates whatever the input is, and the output is supposed to, at the end, is supposed to behave in the way that we want. So we have electrical systems, we have mechanical systems, we have chemical systems, we have economic systems, we have political systems, and we have religious systems. And the list could go on and on. So we are going to be focusing on these. These, the ones below, the economic and political and religious systems. You, because you're alive and you have lived, you would recognize that the input to a religious system and the output. So the input, if they read the Bible to you, and you are the system, there's a certain output that they would expect, and there's no guarantee what the output is going to be. All right. Same thing with political system. I suppose you could say one of the inputs is money and the output. So if a political system, the input is money, and let us say that you are the system, and the output is supposed to be your vote. Again, there's no guarantee that if I put in X amount of money, then this will occur. So these systems that we have down here, we don't study them in signals and systems. They're at best what we call stochastic. These up here, they are called deterministic. So let me just explain a little bit about stochastic and deterministic systems in a simple way. Let me put a definition for stochastic systems and deterministic systems. So if as usual, the mouse will get problem. Don't know where it has gone. Give me a second here. Okay, that part works. All right. So, like I said, I don't know where the mouse gone. It only work with the pen, but not working with the others. All right, so a deterministic system, let me use stochastic first of all. So the parameters, so they use probabilistic module, probabilities. Probably, this is spelled wrong, you know. Whatever. So they use probabilistic modules to determine the parameters. Well, deterministic. In a deterministic system, the parameters of the system are constant. So let me use an example to explain. Okay, mouse come back. So let us say that, so let me give a simple deterministic. You have your system, which is the resistance of the material. Your input is current and your output is voltage. What is the relationship between the output and the input? Is that a trick question to do? So I can answer.
Sir, you don't tell as the volt current is directly proportional to the voltage.
Right. So, but you try make sure say you give an intelligence answer. P equal IR. So R, the resistance there is constant. So V is directly proportional to I, and is the so all you have to do to find V is multiply by the resistance, and the resistance more or less is constant. The stochastic system now, let me put a stochastic system and ask you. So this is Jamaica dollars, and this is my system. And E is the exchange rate. And I'm getting out US dollars. So the what would say the US dollars is equal to Jamaica dollar divided by the exchange rate, no? So what is the exchange rate? How much is it today?
142.
How much will it be tomorrow?
Probably 150.
You notice what the word that you use? Probably. So
Yes, sir.
you have to guess and use. So you have to use probability. When you're calculating the exchange rate. So that is a stochastic system. You can't use deterministic. If I told you in this system say R equal 10 ohms, and I said today, Friday, R equal 10 ohms. Tomorrow, what is R? You're gonna say, but it's the same 10 ohms it's gonna be tomorrow. And Sunday it's gonna be 10 ohms, and Monday it's gonna be 10 ohms, and Tuesday it's gonna be 10 ohms. Unless you probably will say, boy, unless it really, really had to something serious happen. So this, when we say that the parameter of this system, the R, is constant. So this system is called deterministic because your output input relationship V over I, R is a constant. Your output input relationship in this particular case is not the parameter. This thing here, exchange rate, is not a constant, but it depends on the day, and you're going to say probably. So if I tell you for this system, deterministic system, 5 weeks from now, if I put in a current of 2, what am I going to get out? You're going to tell me, say 20. If I tell you 5 weeks from now, I'm going to put in, not practical, but I put in $1,000. How much US I'm going to get? Yes, you're going to say, I don't know. You don't know what we have. Especially like how we are in a very, 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 very volatile time right now. We're expecting a stock market crash anytime here now. So this stochastic system is one that uses probability. The deterministic system, the parameters are constant. There are other types of systems, but we will discuss those later on. All right. So back to what we were saying. So we know this is a stochastic system because that is a whole different level of mathematics. So our consideration for this course is deterministic systems. All right. So deterministic systems are the ones that we are going to use to say to do our calculation. Right? And it is not like the world says that, boy, if you sit down and make them read the Bible or the Quran every day, they will turn radical and blow up themselves and whatever, you don't know. Yeah. Whereas in electrical and mechanical and chemical systems, once you put in a particular input, you must get a particular output. Right? So that's the first thing that I wanted to deal with. All right, so having said that, so let me just digress, as I will do a lot. But let me just digress and say here that in studying a deterministic system, studying these kinds of systems that we have here, are what we're going to do in signals and systems. As you will see, as I'm alluding to, it doesn't only have applications in engineering. It has application in all different aspects of life. So we just always try to tell students, so don't put yourself in an electrical box or a mechanical box or whatever the box that you put yourself in. Don't put yourself in a box. Um, they you have engineers in politics. You have more engineers in banking than you have. Well, not more, but well, let me use a different example. In in Nigeria, let's say one of the things that them have a overabundance of is doctors. In Jamaica, we have an overabundance of teachers and nurses because we have so many teachers colleges and so many places to train nurses. So although we have a shortage of nurses because they leave and go to different climes, but the training system trains teachers and nurses. In the United States, the overabundance is of lawyers. The system trains several lawyers. In France, the overabundance is in engineers. So engineering is considered to be what you could do as your basic degree before you go do anything else. Before you turn doctor, before you turn lawyer, before you turn whatever it is, your basic degree is in engineering. So a Frenchman does not see that, oh, I can only work in engineering. They think engineering is the base that can launch you into any direction that you choose to go. So when consider that, don't put yourself in a box and say I'm only in an electrical engineering box or only in whatever the box that we are trying to place you in at university. The things that we are doing have applications all over the place. Anyhow, so let me first topic that we need to talk about when we have a system to analyze. So let me just deal with that is Laplace transform. If we are going to analyze any system, one of the first things that we need, tools that we need, is the Laplace transform. Anybody remember the definition of a Laplace transform, the mathematical definition of a Laplace transform?
Yes, sir.
There we go. We start to have is integral.
So the integral from 0 to infinity e to the minus st times the function with respect to.
All right. So what the Laplace does is transform. Let me just not technically correct in what we said. What the Laplace transform does is converts calculus to algebra. Yeah, tell anybody said that, Mister. So that we can manipulate the variables much more easily. So that is what it does. It converts the calculus to algebra. That is in mathematics. That is not. Mathematicians love the maths because it is so beautiful and so wonderful to look at, and why it is. But we need it to do some work. So what we do is change the calculus to algebra so that we can proceed to do some things. So so let's just some basic systems. The most well, most I was going to say important, but it's not the most important. The most fundamental function that we have in the Laplace transform is the step function. I don't remember what they call it in maths class. Somebody tell me what they call it in maths class. Let me
Sir.
Heaviside. So let me try to draw a decent line. Yeah. So this is time or time axis. This is 0. This is 1. And this is the function. So u of t mathematically is defined as 1 for t greater than or equal to 0 and 0 everywhere else. Why we are interested in the step function, and we call it a step function, we don't call it Heaviside, is that the step function models, and I'm going to say a step change in the system. So example, if I turn on the light, I turn on a flashlight, the voltage across the filament goes from 0 to 5 volts or 12 volts or whatever the voltage is, and it's going to stay there until I turn it off. So so if you turn on a DC switch or apply a constant force to a system, then we model it by a step function. So at time t, it is t equals 0, it goes to the value and it stays there. So most DC inputs, that is what? All we have to do, if it's 5 volts, there is a 5 u of t if it starts in a time t equals 0. So our step function is the most basic. Like I said, in maths class, we call it Heaviside, which we could never remember the name. So anyhow, so the Laplace transform of the step function. All right, so it's 0 to infinity a to the minus st times, now between 0 and infinity, the value of the function is 1. So it's times 1. And aside a to the ax, when you integrate that, what is it that we get?
One over a e to the ax.
Plus c, but we're leaving out the plus c. All right. So when we integrate this, then this is going to be e to the minus st over minus s, and we integrate it between infinity and 0. So if we plug in infinity in a negative exponential function, then e to the infinity here is going to give me a 0. If plug in 0 inside our function here, then when anything raised to the power 0 is 1. So it's going to be 1 minus 1 over s. So the Laplace transform of the step function is going to be 1 over s. Yep. Can't draw a straight line on this thing to save my life. All right. So the Laplace transform for the step function is 1 over s. But two things: we don't turn on a light switch forever. That is the first thing. So the voltage that we're applying, we don't turn on anything and leave it. But for the rest of time, we turn on something and we have to turn it back off. So so I want to go to now. By the way, anybody writing or I can just
You're writing, sir.
oh, all right. So the need for I didn't make that part of the speech. I go to a nice, quiet Presbyterian church where the pastor preach and you sit down and listen. But for the purposes of this class, this class have to be Pentecostal because I am talking to a computer screen. I'm feeling like I'm getting mad because I'm here talking to myself, so I need some amen from every now and again to say,
Amen, sir. Amen.
okay,
Turn over when the computer got talk back.
okay.
Amen, sir.
Sir, yeah, Mr. Cena go to same church.
Me and Mr. Senior,
Yeah.
Mr.
That's
Senior,
not
I
like
heathen, you know.
the top about amen and all of these things.
No, man, Mr. Senior, I heathen. Him need Jesus.
I'm a virgin still.
Not my own, but he still need Jesus.
So the recording I'm gonna make available.
So you have to talk to the recorder. By the way, am I recording? I should have been recording, but anyhow.
Say, look, I can record, sir.
Let me just check. I did. Wait. I don't see the thing where tell me some recording.
Sorry, it's recording, sir.
All right, cool. All right. So as I was saying, the you know we don't turn on a switch and leave it on forever and ever. It we 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 have some finite things that we deal with. So how do we represent them? So the next thing that we want to talk about is if we turn on the switch at time t equal a, how do we represent it mathematically? All right, so you can tell me when we can move.
Yes, sir, you could move.
All right. So the next one is wait, let me just so call it the step function. So we're saying f of t equal u of t minus a. So the step function with delay.
So which platform we can get the like the syllabus or something on?
I'm going to post it in the WhatsApp group.
Okay.
So ut minus a now. Oh. Ut minus a is 1 for t greater than or equal to a and 0 elsewhere. And so if we're going to find a Laplace transform for that, it's going to be, so it's going to be from 0 to a, e to the minus st. The function is 0 up to there, dt, plus a to infinity from e to the minus st times 1, because the value of the function from we reach a, the value of the function is 1 dt. So now this part here is 0. So this is e to the minus st over minus s between infinity and a. And that, now when you plug in infinity again, that's 0. When you plug in a, you're going to get minus e to the minus, put the a first, alphabetical order, over minus s. So therefore we can say the Laplace transform for u of t minus a is equal to e to the minus as over s. So if I turn on the switch at time t equal a, then if I am using the Laplace transform to model it, then that is what I'm going to see. So we have worked our way to the third one, but we're not going to spending so much time finding out about how you work out Laplace transform. I'm just doing it with these couple to give us an indication. An idea to say that when we're talking about Laplace transform for different systems, then when we're talking about Laplace transform, it is the Laplace transform is to be used to model. Well, it's used to model the input, it's used to model a system, and you can manipulate it to get the output because it's transformed into algebraic, the calculus to algebraic manipulation, which is much easier to do than the calculus. So we're just going to talk about Laplace transform over pulse. So say clear. All right. So now pulse function, we're going to discuss it graphically. So pulse is a signal of finite duration. It starts at time A and ends at time B. So the pulse starts at time A and it ends at time B. So now we want to look and see how it is that what we mathematically, how we write it down, both as in the time domain and in the S domain, the Laplace transform for the function. So we have to look at this function as being made up of two. So we have to look at it as being made up of a function starting at A and another function, a negative function starting at B. All right, so this is 1, 1, minus 1. So if we add everything up to A is 0. So everything up to A is 0. between A and B, the value of the function is 1. And then now after B, it's when we add these two functions, it is 1 plus negative 1, which goes back to 0. So I am a bit distracted here. I'm fooling around with the technology. I'm looking at this thing on my phone to see what I see. And I just realized that when I'm here moving around the thing, I'm not seeing that. So all right. So we know that this function is ut minus a. Here now is negative. So anybody have any guess as to what this function is going to be?
U B minus T.
All right, so we're going to put it like this: minus t minus b. Put the minus outside. This thing always do that. Yeah. So my pulse function f of t is going to be u of t minus a minus u of t minus b. And so the Laplace transform, you can just, we use the capital letter for the Laplace transform, is going to be e to the minus as over s minus e to the minus bs over s, or 1 over s e to the minus as minus e to the minus bs. All right, so this is for a pulse, and then we could go on to talk about a series of pulses. So you're just saying that the mathematical representation for a series of pulses is, and so I mean what the mathematical representation for a pulse is. All right. Like I said, we're not here to work out. Yeah, we're not here to work out the different various Laplace transform, because we have a table for that, and we look up any Laplace transform in the table that we want to look up. All right. So without derivation, impulse function. That's and you just need to mention the impulse function. Somebody tell me. And the symbol for the impulse function is that
Delta.
delta Dirac.
Yeah, okay.
So DIURAC, French name. If I have f t minus a, means that the function is that a starts at a, and it is usually represented as a line. Now, what we use the delta Dirac function. Oh, let me just say what the definition of it is. This is 1 for t equals 0, and 0 everywhere else. And this is equal to 1 for t equal a and 0 everywhere else. So what do we need the impulse function for? Well, the impulse function represents a shock to the system. So example, a lightning strike. Or a punch. Somebody thump you, you would represent that by an impulse function. All right, so it's a very small duration and the value at a particular moment in time, very, very finite, fine, small in time interval. So we represent those kind of things by impulse function. Or noise is usually represented as a series of impulse functions. Meaning to say that if you have a system with noise, then it is represented by the sum of the impulse function. So All right, so let us see, test your understanding by looking at this problem that is here. Now, this thing here, we can say it's between 2 and 3. It's a 5-volt pulse plus a 5-volt spike, because when we add it to this, then we get the 10. So it's a 5-volt pulse plus a 5-volt spike. So what is our f of t going to be equal to? All right, so what is this? What would we write for this in the time domain? Based on what we have discussed earlier.
Or which one, the pulse or the spike?
Pulse.
So sorry, would it be e to the minus 2?
No, you reach f of s already. But
Sorry, u
Oh,
t minus 2 and minus u t no
minus 4, sir.
so wait, it would have been plus u t minus 4.
I'll multiply by how much? Because a 5-volt pulse.
2.
If a 5-volt pulse, so much we have to multiply this by?
Five, sir.
Plus. For the spike now.
5.
It'd be, yeah.
All right. So now, you're saying now the Laplace transform for this would be 5.
E to the minus 2 t 2s. What is
5 e
4 is over this?
minus 4 is well s plus 5.
So that'd be e to the minus.
Yes, sir.
Yes. So this is the Laplace transform that we would have for that. All right. So now we want to write down 2 more Laplace transform for this evening. So the Laplace transform of a derivative. You want to write it down for the first derivative. So you want to write down Laplace transform of f prime of t. For this, we're going to need integration by parts. Mr. Silva, we don't see him from mine. All right. Integration by parts. Remind me how this going on.
Then, yeah. So they have uv minus the integral of v du.
So u v minus the integral of v du. All right. So if we apply that, it's e to the minus st f prime t dt. This is my classic u dv. So it's u, sorry, e to the minus st. This is a derivative, so the integral of the derivative is just a function itself. Minus the integral of v. V is, and then when you differentiate this, so the du, let me put this first, the du first. Let's get to it. When you differentiate e to the minus st, the coefficient of t goes on the front, so that's minus s, e to the minus st. And v now would be f of t dt. Plug in infinity inside here. Infinity, this means this is 0. Minus. Plug in 0 inside here. This is 0 inside for t. E to the 0 is 1. So, and t is 0 here. So we just put down f of 0. And take the minus and the s outside. So constant. So plus e to the minus st f of t dt. So we see that this is f of 0 plus, but this is the original definition of Laplace transform. So it's just s f of s. So the Laplace transform for the derivative of a function is s f of s plus or minus f of 0. Let me write it in the way that you normally would see it. We dry it fast to make it little better, but not much. It only fix itself. So give me a second. All right. So the next one that I want to do is, oh, before this, f of 0 is called the initial condition. Of the system. Not coming back to you, take come for the lecture because every minute somebody, excuse me 1 second. All right, sorry about that again. You don't believe so from the class start is 15 missed call. When I'm at home, nobody don't call me. All right. So we want the Laplace transform for the second derivative. So the same thing, infinity 0 e to the minus st, and then it's f double prime of t dt. So we're going to use the same u dv argument. So that's u and when we integrate the second derivative, we get the first derivative. So this is going to be f prime of t minus the integral in 0 infinity of v, we put it out here, so du. So plug in infinity inside, so you get 0. Plug in 0, get 1, and then this is f prime of 0 plus s, and then this is the integral between infinity and 0 of e to the minus st f prime t dt. But we already worked out that already. We have the answer from up here. So this is going to be minus f prime 0 plus s, and we know the answer is going to be s f of s minus f of 0. So the Laplace transform of f double prime of t is equal to s squared f of s minus s f of 0 minus, whoa.
You're welcome. At Frontier, we strive to make continuous improvement based on
Minus f prime of 0.
my goal is to satisfaction. Have I resolved the reason for the call today?
All right. All right. So second derivative. So these again are called the initial conditions of the system. No, like I said, maths people look at these things from the beauty of the mathematics. I was explaining some of the problems that we have with mathematics is because you have different philosophies all over the world for different um, how maths is done. And one of the things that I have discovered, I've found out, I realized, is that Americans teach maths by topic. So then teach you maths mix up. Not by topic, by problem. So you need to know to do this, you need to know to do that, you need to know to do this. This is a particular problem, you need to know to do it. The British and Europeans teach it by topic. So you need to know Laplace transform, you need to know algebra, you need to know to know geometry and then trigonometry, and then teach it in blocks. African and African derivative people tend to teach to learn maths by what practical situation it arises from. So they always want to know, so what may I learn this for? Where we can take this and apply this? So we are never normally interested in the beauty of the we always want to know what we can do. Or what is this? All this is in aid of. So what I'm saying now is that it's all well and good, we know the derivative and we know how to, but the real reason why we are studying this in signals class is because we have some circuit elements. We have a resistor, and we know that when you pass a current I through it, you get a voltage. So we know that V is equal to IR. We have another circuit element called an inductor, L, and when you pass a current I through it, what's the relationship between L, I, and V? Anybody remember?
Sorry, I get SL.
Yeah, but they're meeting at a time domain.
It would be the integral of I dt. L, the integral of I dt. Or yeah, sorry, yeah, di by dt, sorry.
All right. So the voltage for coil of wire change when the current change at the rate at which the current change. So if your spark plug generates a high voltage because you turn on the current in the coil, and because there's a rapid change when you make a step. So if you go from this, the rate of change for step is very high, so you get a very large voltage out. All right, so your coil, any coil of wire, the voltage that you get when you pass a current through it depends on how fast the rate at which the current is changing. And then there's another one now, the capacitor. Anybody know that one?
Sorry, I guess me that mix it up, you know.
Right.
I think I know 1 over C, sir.
1 over C, the integral
Integral of 1 over C.
I.
I think it's dt. Yeah. Oh yes, sir. I dt.
Mm-hmm. So now, I want to make an analogy and ask a question. So I'm going to put f of t and put f of s. And consider the initial conditions to be 0. So this is to be in the middle. So f of t, the Laplace transform is f of s. F prime of t is s f of s. F double prime of t is s squared f of s. I'm ignoring the initial conditions. So f triple prime of t, what do you think it would be?
S cube f of s.
S cube f of s. So each of them is one step. So what do you think the integral of f of t would be? This is s cubed squared 3210. So what do you think this would have been when you reach the integral? integrate going one step each time. So what do you think this would be by analogy? This is 3, this is 2, this is 1, this is 0.
Sure. 1 over S.
All right, so s to the minus 1 or 1 over s, f of s. All right, so the integral is the function divided by s. So we want to make the analogy. So this is vs equal to I of s times r. This is vs. If we were to take the Laplace transform now, this would be SL, and the derivative, this is the derivative. The derivative of a function is s times whatever the function is. So we're going to say this is the dt is the derivative, so that's going to be s is. And then this one here is vs is equal to 1 upon c. And now the integral is the function over s. So therefore it is I s over s. So now, so one of the things now, we can, if we look at change the domain, this is R, this is IS, this is VS. But this one, this is IS, this is VS, and what is there now is, well, we normally put S before the L, the common S capital L, so I suppose that's why. So the relationship between voltage and current is V over I is equal to SL. And then this one here, the capacitor, we have a current IS, the voltage VS. So therefore we can use this as 1 upon CS. So what that allows us to do is that when we have a circuit, so for example, if we have a circuit, so we get to take that circuit and treat it. Like I said, if we were to do it in the time domain, then what we would have to do is use calculus methods to work out the value for I. But now, when we go into the S, we can take this circuit and put it in the Laplace domain and work out what the value of the current is. Because we can replace each of these things by its S equivalent. So what I mean by that is, first of all, the 10-volt DC source, what would we write for that in the S domain?
So it wouldn't be just 10, sir.
Mhm.
For the
Think again. The DC source. So when you flip the switch, you're going to get 10 volts constant across the circuit.
Or would the
You start, I'm gonna hear the rest of it, what you said. Now that sound like it was going to be the right answer.
sir, the heavy side, sir, the step function.
That will be 10 over S.
Yes, sir, something like that.
Right, the step function, so it will be 10 over S.
Sir, isn't that the same as like a Laplace of a constant?
Mm-hmm. Remember, say, let me go way back up here. The Laplace of, that's one thing we have to clean the board. Remember, like you said, the first thing, the Laplace of the constant. This is the constant that we have up here. This is the constant. So the Laplace of a constant is 1 over S. So if this was 10, then it will be 10 over S. So the Laplace transform of a constant is the constant divided by S. If it was all right, so this constant, we're going to replace it by 10 over S. If it's a constant value, then we're going to replace it by the value over S. Now, the inductance is going to be replaced by L times S. So L now is 2. So therefore, we replace that by 2S. The resistance is just R. The voltage current relationship in the S domain is just R. So that's 10. And the capacitor,
X over 5.
okay.
1 over S5.
So now, so we said that we can't just treat it as a series circuit. So we just add up, we put everything over 5S. So that is 10S squared plus 10 5 is 50S. And I put in S squared. This is S plus 1. So now, if I want the current, so I of S is equal to So we know V equal IR.
Yes,
So,
sir.
so therefore it's going to be V of S divided by, is not,
ZT,
right.
the impedance.
So that's 10 over S divided by 10 S squared plus 50S plus 1 over 5S. So that is equal to 10 over S times 5S over 10S squared plus 50S plus 1. Is equal to 50. So 50 over 10 S squared plus 50 S plus 1.
Yes, sir.
All right. And then now we would have to use algebra to convert that. So we're going to do 5. We divide everybody by 10. So 10, sorry. So that's S squared plus 5S plus 1 over 10. So we would have to look up in Laplace transform tables to convert that back. So let me find a Laplace transform table.
Sir, could you scroll up back a bit?
Yeah. Okay. Further still.
No, that's good. That's good.
All right, tell me when we can.
Sorry, so the videos, the recording will be posted in the WhatsApp group as well.
Yeah, yeah.
Yeah,
Well,
man.
I
Tap
will,
post on it there.
all right. So let me just go to the Laplace table to write down the one that I want to write down. Um, and just give me a second. It give me some issues. Give me 1 second. All right. We finish writing what we're supposed to write.
Yeah, Minister.
All right. I'm going to complete the square on this. I teach at a high school, so teach some high school pretty much from time to time. So I can't bother. Completing the square is one of those things that. So it's half of. I don't know. Never see one yet. It's half of this plus 110 minus whatever is inside here, so squared. 5/2 squared.
Sir, if you have a calculator that does all the computations, that's fine, right?
Yep. So you have a calculator to complete the square for you?
Yes, sir.
Mm-hmm.
Yeah, man.
Never hear about it yet. But then me behind time.
Yes, sir.
See me still here, I multiply by 4 and all of them foolishness here. So 25/4. Really? 246. Then use the calculator and tell me what it get.
Alright, sir. S1.
I know the roots we want to know. We want to complete the square.
All right, sir. S plus 5/2 all squared minus 123/20.
Sure. All right. So now, let me just go to the table and say which one it is that we need to use. So we'll go to our table. And the Laplace transform, I have to fix this when I get it. When I send it to, I'll fix this before I send it. All right, this one is so wrong. This one here is wrong. What we want to use is the one that says A, when we complete the square, B squared. But I think I have a problem. I need a bigger hammer. Because um 5/2 1/10 minus 1/23. Yeah, I need a bigger hammer. I need a stronger Laplace transform table, the one with Shiner, Kosh, Kasha, and them something there. Because so let me explain why. See, this is a plus, and it should in our thing we have a minus. When you have a minus, you're going to end up with a different kind of function. So it's a bit of a problem, which I don't really want to deal with that this in the first class. So I'm going to leave it here and say, and next week we work it out. Show you the table and use that we will use and work it out. Yeah, I'm gonna look for the table. We'll look for it. No, see, nowadays on the net though, everything then telling us say, oh, if you want to use this, so let me go to the table. If you want to use this, you have to sign up this and you have to by the way, other more than know, what's the deal with WhatsApp on February the 6th? Is only India alone?
Yes, sir.
So no, go on, sir. Everything good with WhatsApp, sir. Everything good with it, sir.
Why? Them change their mind?
No, sir, them not change their mind, sir. People just overreact, sir. Say no, people just overreact, sir.
So what's basically happening with WhatsApp right now is that they want your permission to share your phone data with Facebook itself. So they want to know all the people you're talking to, where you're traveling, your buying habits, because they're looking to certain countries like India with the transactions over the phone. So then they want access to log your purchase history and all them something there and send it off to Facebook.
And then
of course, uncomfortable because
sir, but the thing is, it been happening for a long time, as even sir. Well, I don't know about it, so I don't know why people are being so sir.
Well, I think the Indians are up in arms.
Sir, them basically are doing it for advertisement purposes. Because them been do it before, them just make you know that time.
So I'm going to say that you're sure? Because nowadays, what am I looking for? Oh.
Spider-Man try spy upon me.
But them been a spy upon right now, them a spy upon sir class. If sir I teach good hour.
Yeah, man. Yeah, man. Them all right.
Sir, you're being watched.
I've always been watched. From you have on your computer, you turn on your screen, they know every website where you go to.
Yeah, man, some don't know why people abuse us, sir.
No, there's a reason why people abuse so. And I understand why people abuse so. Because, like I say, it's 400 million Indians use WhatsApp, I'm being told. And the reason why them upset is because them say, the same Facebook say, same WhatsApp say them not. Europeans are exempt. But if Indians don't agree to it, then they're going to delete them WhatsApp account. So I was wondering if we are also, which list we in, the exempt list or because if you say Indians use their phone and buy things, in Kenya, they use their phone and pay for everything. Them transfer credit as currency. meaning that me take up my phone and say, all right, me send X amount of, it's not credit, but them use it as credit. Them use the credit as a money transfer system. So they transfer it and pay for it. So they go supermarket and you take up your phone, and then the person cashing out take up their phone and you transfer the money to their phone. You transfer the credit or transfer whatever it is them having a
Sorry,
credit.
they call it cryptocurrency.
And in a really cryptocurrency. But yeah, it's a form of cryptocurrency. But another one, another World Economic Forum,
Sir,
first
cryptocurrency.
world cryptocurrency.
Sir, cryptocurrency are only one that is not bound by any government. So it
Ah.
just so the Jamaican government are gonna have one too, but it's not cryptocurrency. Then call it digital currency.
So we're getting rid of money as we know it, right?
Yeah.
And so this money that you have and I have, what is it going to be? A form of imagination?
Yes, sir.
Something in our cloud?
Yes, sir. Because they want to know how you spend. Sir, it's a whole economic thing, sir. Yeah.
Reset. So
they say studies show that that a country that use more online not less physical cash, the economic grow much better because I guess they can trace the transaction and they can properly collect taxes. So when me and you draw out your money out of the bank, they can't tell you what we do with it.
So
Because
why
in the economy?
we have some question? I have questions. Who is them who can tell what we do with it?
The Minister of Finance.
Your girlfriend, your mother, your
My
father.
girlfriend and my mother no business what me do with the money.
Oh, so why the Minister of Finance business?
Because they want to know that if me do a transaction with anybody, that person will pay tax, so they can collect for their money.
Okay. So they can collect their money off all the transactions. So
I think it's more than that still.
Because that no seem
logical.
Like a good enough reason. Because they are collecting tax off of all the money.
No, sir, but you have some person like sir, them a target like small business, like all the man who sell cane on the roadside. Him not have a bank account, therefore him not have to pay tax. Him get pay money go straight in the government.
But
now
him still pay tax somehow.
Them probably pay tax indirectly, but they want a more direct taxation because like unlike Mr. Fraser wouldn't pay tax through income tax, right? And then when you go to the supermarket and buy anything, you pay more tax again. So therefore, if the man on the roadside, him a go to supermarket and pay tax, but therefore within fee business transaction money coming in a fee pocket, him not paying a tax through that.
But look at it this way. Remember, I said remember the threshold is 1.5. In that man on the roadside selling cane not making 1.5 per year.
Yeah, but that is true. But therefore,
income tax, you have to pay income tax here.
But remember, say if a man, if you're doing business, for you to get one of those swipe card machine where you use by NCB, you need to have a registered business, and they want to have every small business to have a registered business, so they can actually.
So they can keep a track of all businesses.
Yes.
Not necessarily money.
So
and therefore money not leave out of the country with anybody, no.
No, money can't leave out of the country so easily.
If you have it physically, you can do it. But
yeah, man, because it's like China and United States.
Even if you bring the money physically out of the country, the value is still here. That little number on it, that's the value. So they
But
can
if
always
it's
print the
out,
next money with the same.
but if
Right.
it's out of the economy, because economic circle or macroeconomy, well, them have to pay money to replace that money. So I guess.
But not so like I can't carry my Jamaican dollars go anywhere. I can't go in the bank, take up my money and say I carry the 200,000 Jamaican dollars to the United States. It's have no use there.
No, so you have to convert that. So
So I'd have to go to the bank, convert it,
get some.
pay whatever it is, and there's a trail that says that him convert it to whatever. There's a trail that says he left the island with whatever. So I am still not convinced.
Sir,
Because me seeing online where they're talking about say you will own nothing by 2030. You will own nothing and you will be happy.
So what about the
And it's highly unlikely.
But that I will be happy or that I will own nothing.
That we will be own nothing.
Sir, if you own nothing, that means you owe nobody. You don't have to borrow anything. Cause you don't own nothing.
But
But
the
that
country
doesn't make sense, sir. Countries like America are based on the credit system.
Mm-hmm.
So how
but they still own things.
How will their economy survive if there isn't credit? And credit.
But the average Americans live on debt, you know.
Exactly.
You know that.
So
Exactly.
So why you want to put the rest of us in that situation? We have to rent everything.
Or happiness is not dependent on what we borrow, sir.
No, our happiness is dependent on the relationships that we have.
Exactly.
What if you borrow a relationship?
If I borrow a relationship, it's still a relationship. But
my thing about the cryptocurrency still, sir, for instance, the vaccine thing, when they try to instigate for everybody, they have to take it. So if you say them want coming with the cryptocurrency, so anything them say, you have to do it, else them freeze the money.
Microsoft already sort out that, you know, with the cryptocurrency, you know, that if you look up patent number 060606 2020 060606 is a thing that Microsoft has developed. 2020-666. Microsoft developed a
mark of the beast.
Well, you can read about it. Is it going to monitor all of your body fluids? So some people are alarmed because them say when it monitor all of your body fluids and your heart rate and all of those things, then they will have access to your deepest and most personal information. Because they will say, if you're monitoring somebody's heart rate, then you can tell when they have sex, when they asleep,
Sir,
when they eat. Huh?
I think that's a lie, sir.
What?
Because I actually tried to do a polygraph test before, but I think at one point the person who conduct it get confused. I'll be confused too.
Yeah, you see, the thing about it is, there are certain things that, like we said, I read the document and it said that they're going to monitor all your body fluids. So it's going to take it, body fluids and body parameters, temperature, pressure, those things, heart rate, and it's going to turn it into cryptocurrency. So I don't know what that is all about, but all I know is that is the patent number is 2020 060606, and it's supposed to be able to do all of those things. It's supposed to be something that they implant in your body and monitor you. So if you know when you're sick, I know when you're healthy. I know what activities you were pursuing. If you are run, if you are walk, if you are. So some persons say that is too much of an invasion of their privacy. For you to know all of these details, because if you download all of that information and you can tell all of those things, then now on top of that, with China introducing what is called social credit. So your behavior is going to determine how much credits you have and what you can do and cannot do. Anyhow, we were talking about that most of the time in all the world up until now, change has not been forced on anybody. Person look at it and say, this is better. So we used to have landline and them come in with cell phone and then everybody say, we want a cell phone. And as them upgrade, people say they want it. So I don't see why you need to force something on somebody if they don't think it is something that them would be useful to them. Because everybody born with a brain and can look at and evaluate the situation and say, yeah, I want this or I don't want this. So this force change that I see coming at us, I am not sure it's going to work because people are going to resist it.
Yes, sir. Force change bring resistance, sir. That you know.
So people are going to resist it because they're not going to look at it as something that they want. And privacy is something that is important to all of us. So I don't know why. And some of us, not like me included, are very suspicious of the World Health Organization because Bill Gates is the major funder. Now that United States has pulled out. I suppose now that Biden is going to come in, that they're going to go back in as the major funder of WHO. But Trump pulled out of WHO, so Bill Gates became the de facto major funder of the World Health Organization. And him pushing vaccination, saying he wanted to vaccinate everybody. But one of the problems that they have with him in Africa is that he was funding some vaccinations for some people in Kenya in 2015. Some women in Kenya, and then find out that the vaccine have HCG in it. And what HCG is a sterilization drug. Means that you can't have no picnic. And he has stated many times that his aim is to reduce the population of Africa by 100 to 150 million from its present value number today. I think you can have a man like that around the WHO or call the shots. Shine, this is equal to B over S minus A squared minus B squared. So when it's plus is sine, when it's minus is shine. So maybe we just finish to work out the problem because that was the last thing that we did have to do. So let me go back. And go back here. So so the thing says e to the at shine bt is equal to b over s minus a squared minus b squared. So in our case now, a is equal to minus 5 over 2 and b is equal to the square root of 123 over 20. So therefore, IT is going to be equal to, well, this 5 is here, so that 5 is going to stay. E to the minus 5 over 2 T shine B 123 over 20 T. So that would be our shine, S-I-N-H. So but well, only thing when we talk to them, because we was afraid because they say the problem that maybe is the community where we live in. And most of the young people in the community, the only thing they care about is iPhone and the jeans that them wear, and the man them whichever girl them a talk to. So I say we are going to get caught in this thing. So this thing never works. And it works out to 2.48. So this generation not informing themselves. Your generation not informing on yourself about anything. You know, we are right. We have what we'll already. So we is one of them want control that we. And we out.
Sir, I go bust a Patrick Star, sir. You know me I talk, sir, I go live under one rock, sir.
Oh.
In the way I go bust, sir. Say my find my rock, me I go live under already, sir. Just smooth it out more, sir.
Which part is there?
Sir, me can't tell you that, sir. Remember, say them I watch you, sir.
Oh yes, so yes, so yes. So they
Yes,
might
sir,
have
me
come there
can't
for you.
Just know say my find my rock, sir.
When you was a little boy, they used to have someone live up our Hill, you know. Every week, they used to dynamite the cave them where they live in. Until the man they get some gun and start shoot back after the police. And then so they stop go up there. Because that whole man used to live up there. So I don't know if I wanted the cave them. Or Bobo Hill in a Bull Bay. No police no bother go up there, so. Alright, so. Anyhow, we stop it here for today. We're going to continue next week. Work out some more problems. With using Laplace transform.
Okay, sir.
Sir.
So we can come at the office now, sir.
Yeah, I'm upstairs.
All right.
Electrical.
Oh, sir, we have to check Miss Dunkley then to get here.
So, sir, you're going to post this recording?
Yeah.
Oh, Nicola,
Are you going to post them every week, or is somebody else going to post them?
I post it.
Yeah, but editor incriminating.
Post them in the classroom or something so that we can refer back to them instead of just putting it in the WhatsApp group.
Sir, you create the thing, sir, the Canvas classroom already, sir?
It's going to be on YouTube.
Yeah, so I create the Canvas classroom already, yeah. So I'll just give you the join code. I will send the join code in the group.
Okay. Just send it in the group, in the WhatsApp group though. Well, it's the link I go connect us to YouTube anyways, but remember sir don't have that much followers and viewers, so it's difficult to go search him and find him on YouTube.
Well, what we do is use I will find this in the WhatsApp, when you post it to YouTube, I will put it in the Canvas group.
Okay, sir.
I just link it in the Canvas group.
Okay.
All right, sir.
All right. So next week.
All right, sir.